Problems and particle equilibrium. Here the question is, a sphere of weight 100 Newton is tied to a smooth wall by a string as shown in the figure. Find the tension in the string and reaction of the wall. We have to find out the tension in this string and also the reaction exerted by this wall on this sphere. Here it is given that it is tied to a smooth wall by a string. That implies that this sphere is at rest. So we can apply equations of equilibrium. That is, we can write sigma fx equal to 0, sigma fi equal to 0. That is two equations, and we can solve for the two unknowns, that is for tension in the string and for reaction of the wall. So for that we need to draw the free body diagram. So the solution here, so draw this sphere first, and then now the sphere is in contact with this wall, vertical wall, and whenever two bodies are in contact with each other, then there exist two reaction forces. One reaction force will act at tangent to the contact surface, and the other reaction will be normal to the contact surface. The the reaction force which is tangent to the contact surface is called as the frictional force, and the reaction force normal to the contact surface is called as the normal reaction. In this case it is given that the vertical wall is smooth. That implies there is no friction, there is no tangential reaction exerted by this wall on the sphere. Now here we are interested in the sphere. That implies we are going to draw the free body diagram for this sphere. Now this this sphere is in contact with this vertical wall and also with this string. Now remove this vertical wall and show the reactions exerted by this vertical wall on the sphere. In this case there exists only the normal reaction, and show the normal reaction exerted by this vertical wall on the sphere. So this is the point of contact here, and this is the tangent. So now the normal reaction will be normal to this tangent here, and which will this reaction force will pass to the center of the sphere from the geometry of the sphere, which is like a circle in this case here. Now remove this string and show the reaction exerted by the string on the sphere. Here in this case the sphere will pull this string in this direction, and the wall here at this point will pull this string in this direction. Thereby the string will be tight and tension will be developed in the string. Simultaneously, when the sphere is pulling this string in this downward direction, the same time the string also pulls the sphere in the upward direction, but with the same magnitude, that is along this string. Now remove this string and show the reaction exerted by this string on the sphere. That is nothing but the tension. Now this tension will be in this direction. And also show the self weight of this sphere, which is going to act always vertically downwards towards the center of the earth. Now here we have removed all the contact bodies with which this sphere is in contact, and shown the reaction forces exerted by those contact bodies on the sphere. So we have considered all the forces acting on the sphere. Now this resultant diagram is called as the free body diagram. As there are no dimensions given for the sphere in the problem, we can assume this sphere as a point object like shown here, and then we can show all these forces, so which simplifies like this. So here this is the sphere which is assumed as a point object, and its weight is acting vertically downward 100 newton, and we have assumed that the normal reaction force exerted by the vertical wall is in this direction, normal to this tangent here, and the tension is acting in this direction, making an angle 15 degree with this one. Now since this sphere is at rest, we can write equations of equilibrium. For that, we need to resolve all the forces along x and y axis. So in this case here, 100 Newton is already acting along y axis, so no need to resolve this force. Similarly, this reaction force R is acting along x axis, so no need to resolve it. This tension force here, it is inclined one, so we need to resolve this along x and y axis. Here this tension T is making an angle 15 degrees with this one, so this component will become cos component. The two components are, one will be this, another will be this, and as this direction of this tension is acting away from this point, both the component direction also act away from this point. So here the two components are, one is the t cos 15, so this will become t cos 15 and this will become t sin 15. So they are shown here. Now after this, here we can write sigma fx equal to 0, since this sphere is at rest. So the net force acting in x direction is 0, that is sigma fx equal to 0. And from this figure here, that is we'll get this is r plus r minus t sin 15 is equal to 0, equation 1, and writing sigma fy equal to 0 because the sphere is not moving along y direction, so net force along y direction must be equal to 0. That is equal to algebraic sum of y components of all the forces acting on the sphere along y direction must be equal to 0. Then we'll get this equation equal to, that is t cos 15 minus 100 equal to 0, equation 2. Now solving this equation 1 and 2, we get tension T in the string is equal to 103.53 Newton, and the reaction force exerted by this vertical wall on the sphere is equal to 26.79 Newton. Here we have assumed that the direction of the reaction exerted by the wall on the sphere as along positive x-axis. So one may also assume the direction of R along negative x-axis. Then we get in that case, then we get R equal to minus 26.79 Newton. In this case we got R equal to plus 26.79 Newton. It means that the assumed direction of R is correct. We have assumed that R is acting along positive x-axis direction, and we got R value plus 26.79, means the assumed direction is correct. If we assume the R direction along negative x-axis, then we'll get R equal to minus 26.79 Newton. That means the minus indicates that the assumed direction is wrong, and that force is going to act opposite to that assumed direction. And if you are substituting these values, R values, we need to substitute whatever value we get. That is, if we get R equal to plus 26.79, then substitute plus 26.79 in that equation. And if we get R equal to minus 26.79 Newton, then substitute minus 26.79 Newton in any equation when you are solving for the other unknowns. So this completes the problem.